In this video, I'm going to show you how to use the programs for Bayesian additive regression trees, or for short, BART. I assume you've read the material for it in Chapter 15 and the material on Bayesian modeling in Chapter 8. In contrast to most regression models, BART uses regression trees as the basis for predicting outcomes from a set of predictors. It does not assume linearity and can readily detect and reveal both linear and nonlinear relationships in data. There are different forms of regression tree modeling, but the two BART programs I consider rely on Bayesian frameworks, which separates them from other regression tree modeling methods. I provide two programs for BART. One program uses the general BART framework that allows you to examine the same types of models you would work with traditional multiple regression. The second program is a specialized version of BART that was developed for the analysis of causal links between a binary independent variable and a binary or continuous outcome while controlling for a host of nuisance variables that I'll refer to as covariates. I usually use the first program, called BART, to analyze the relationships between continuous mediators and outcomes. I use the second program, called BART2, to analyze the effects of the treatment condition on a mediator or the outcome. My goal here is to show you how to use the programs mainly by discussing program output. For descriptions of the logic of BART analyses per se, see Chapter 15. Here is the influence diagram for the example I will use. I omit covariates to simplify the diagram, but in the examples I will show you, I include two of them for the treatment to mediator link and two other covariates for the mediator to outcome link. The covariates are treated as exogenous and all are measured at baseline. The two mediators are assumed to reflect the primary mechanisms by which the treatment condition influences the outcome. Hence, there's no direct effect from the treatment condition to Y. I can, of course, test the viability of this assumption with the data, but on an a priori basis in this particular study, I do not expect the direct effect of the treatment on the outcome over and above the mediators to be of consequence. Y is measured on a metric from 0 to 50. M1 is negatively related to Y and is scored on a 0 to 40 metric. M2 has a positive association with Y and is measured on a 0 to 10 metric. All measures are multi-item scales. The overall sample size is 442. In Chapter 15, I walk you through the entire RET analysis, but here I only focus on parts of it for purposes of explaining program output. The programs have some output in common, so I'll explain those first using the BART program for mediation analysis. The same output appears in the BART2 program, so you need to familiarize yourself with it no matter which program you use. Also, the two programs have many common input parameters. Let's go access the program. I scroll down till I see the button that says BART. That's down here. When I click on it, a set of instructions appears in the description box that explains how to use the program. I'm not going to go through this box with you because I'm going to show you how to use the program here in this video. Further down is the input box for the program over here. And this is where I instruct the computer as to the parameters of the analysis that I'm going to be working with. Because I'm going to be analyzing raw data, I have to go get the data file. So I'm going to do that over here. I'm going to click on Choose File. That will take me to a browsing window, and I browse to the folder and file where the data are stored. And that's going to be the data right here. So I'll open that. The computer grabs the data file and shows me the names of the variables in the file. This is very important to have access to because I'm going to have to refer to some of these variables in the input values box. R is case sensitive, and I need to make sure I respect the capitalization of the variable names, and I need to spell the names correctly. Up here, I type in the full folder path where the file is located, and I repeat the name of the file. And then I'm ready to go. In both programs, you choose a predictor that you want to do a more detailed analysis on. In the Bart program, it will usually be one of the mediators. And in the Bart 2 program, it will be the binary treatment condition dummy variable. I'm going to use med2 in this case, the second mediator. I'll explain this second box later after I can put it in better context of the output to be discussed. For now, we'll leave it blank, and in fact, for most analyses you do, you will just leave it blank. This box is the outcome type, which can be either 1 for binary or 2 for continuous. The default is continuous, which is 2. The numerical codes are in the description box, but if you forget them, you can press the toggle button down here, and it will remind you of the numerical codes. This box is the percent confidence intervals you want to work with. And these 3 boxes here have to do with parameters for Bayes modeling. I discussed them in Chapter 8. I specify a set of default values for them that will work well in a wide range of situations. But some methodologists like to fine-tune or quote-unquote tune them by altering the values somewhat. See my discussion of them in chapters 8 and 15. I then enter the equation down here using our format that I want to analyze. I'm going to delete this. I'm going to put in the regression equation, so the outcome is going to be y. And I'm going to predict that from med1 plus med2 plus the 2 covariates. So I have the outcome on the left. Instead of an equal sign, I have this little squiggly tilde here. And then I list the predictors on the right, separated by plus marks. And that's the equation I'm going to estimate. It's very important in the equation that you include the target predictor up here. And that's true in both programs. Make sure your equation is complete. To run the program, I would click Register Input. My website will generate the R syntax you'll need to conduct the analysis. You copy that to the clipboard. You open up R. Then up here on the left, you'll enter Control V and the syntax will paste. And as it pastes, it will execute and the program will run. Now the program runs very slow, and so you have to be patient. I'm going to skip ahead and go directly to the output instead of making us sit here and wait for it to finish. Okay, so the output is in blue and the syntax is in red. So I'm going to move up to the beginning where the output starts. Now both programs will give you a set of descriptive statistics for the variables in your model. Those are shown here. You'll also be shown the results of a traditional OLS linear regression, and that occurs here. That's just in case it's of interest to you. Here are the predictors here with a ZX in front of them, which you can ignore, and the outcome is Y. These are the regression coefficients, the standard errors, t-values, and p-values. Now both programs will give you diagnostics for model checking. With continuous outcomes, the Bart model technically assumes normally distributed errors, although it is fairly robust to violations of the assumption. One diagnostic reported by the program is a normal QQ plot of the y minus y hat residuals. It looks like this. The quantiles for a normal distribution are listed on the x-axis, and the observed quantiles for the residuals appear on the y-axis. The data point should roughly approximate an increasing straight line across the plot, as indicated here by this blue line. That's roughly the case here, where the residuals are falling along this line. A few minor exceptions at the top and bottom. Another plot that is provided is a classic trace plot of the error variances during the Bayesian Markov chain Monte Carlo iterative process, also known as the MC-MC iteration process. I described this plot in the appendix of Chapter 8. The plot is rather technical, but it essentially is a type of time series plot that shows the values of the estimated parameter as the MC-MC algorithm iterates, helping to assess the convergence and mixing of Markov chains. Trace plots are used to visually evaluate if the Markov chain algorithm has converged to the target posterior distribution and that it's no longer influenced by the starting values for the search process. In a trace plot, if you see a distinct extended descending or ascending trend in the sample values across the iterations, like this one here, this means that the MC-MC process is not yet stabilized. A horizontal trend with seemingly random fluctuations about it suggests stabilization, and you see that here. When we work with the posterior distribution in Bayesian analysis, it's common to discard the initial set of sampled values until the process is stabilized. The initial phase is known as the burn-in. In the plot, I signify the burn-in stage with the red line here. I basically told the program that the first 100 trials we would treat as burn-ins. The Bart package in R can produce trace plots for any parameter in the model. To economize, I only report the one for error variability, but you can dig deeper than this once you become familiar with the R package outside of my simplified implementation of it on the website. Both programs also present a scatter plot of the predicted y-scores for each individual versus the observed y-scores. That's to help evaluate model fit. Albeit, the two programs use somewhat different formats, and I'm showing you here the format for the Bart program, but they're both obvious. The histograms for y and the predicted y are in the diagonals. Y Bart are the predicted y's here. The correlation between the predicted and observed values are in the upper off diagonal, which was quite high, 0.95, and the scatter plot with a smoother as a red line is in the lower off diagonal down here. In addition, both programs report the model root mean square error. Here's an example of the output for the current analysis. The root mean square error, or RMSE, is an index of the average discrepancy between the predicted and observed values. The lowest value it can have is 0, and the lower the value, the better. For the Bart model, the average disparity between the predicted and observed y, where y is measured on a 0 to 40 metric, was 2.05 units. This improves on the RMSE for the traditional linear model, which was 3.36. The reason Bart is lower in this case is because some of the variables are non-linearly related to y, and Bart is sensitive to that. Linear regression is not. To the right are the correlations between the predicted and observed values for each of the two model types, the Bart model and the linear model. The results for the current data tend to favor the Bart model in terms of the prediction of y. In addition to the above, both programs also report indices of the relative importance of the predictors in the equation in influencing y. Variable importance of a given predictor is indexed by documenting how involved the predictor was in defining branches in the regression trees underlying model predictions. For statistical details of this index, see Chapter 15. The index is expressed as a proportion, reflecting the proportion of times each predictor was used as a split point in the regression trees in the posterior sampling process. The logic is that if a predictor is important, it should appear more often in the fitted trees. This is a plot of the predictor importance produced by the program. In this case, the first mediator was the most important, appearing in almost 40% of the branches. The second mediator was second most important, and then we have the two covariates down here. Now, some methodologists argue that this index is too crude and not all that helpful, and that it lacks a solid theoretical basis. So you might see this appear in the literature, but a lot of people stay away from it. Final plot that is provided, but only in the Bart program, not in the Bart 2 program, is a partial dependency plot. This plots the predicted covariate controlled expected value of y as a function of the target predictor, in this case the second mediator. When I look at this plot and I look at the general trend, I can see that there's a curvilinear relationship between scores on the mediator and the predicted outcomes. At lower scores, the curve is relatively flat, and then it turns upward and increases dramatically up until the very top where it looks like it's flattening out. So this plot is giving you a sense of the relationship between the mediator and the outcome. Now, when we interpret these plots, we usually don't interpret every little wiggle in the plot. We're looking at the general trend that is operating. The plot is usually complemented in the program by a table of values that were used to generate the plot. Here are some selected entries from the table that the program generated. Here are the scores on the second mediator. Here's the predicted y value, and you can see those are relatively flat until we hit a value of around 6.5, and then there's the curve upward and the flattening out. And then these are 95% intervals for each one of those predicted y. Now this plot and table is not generated in the Bart 2 program. This is because the target variable in Bart 2 is the binary treatment variable, in which we want to see the effect of the treatment on the mediator or the effect of the treatment on the outcome. Going back to the program, if I want to see what the plot looks like for the first mediator, I would rerun the analysis, but now under target predictor, I would change that to the name for the first mediator. Whatever variable you name as the target predictor, that's what you're going to get the plot for. Now, sometimes when we look at the tabled values, we don't get a value of the mediator that we are particularly interested in. And let's suppose I want to do an analysis where I focus in on that particular value and see what the predicted y is for it. That's what this box is for here. If I put in the target value, say of 5.0, then the program will generate information for that specific target value. Okay, let's look at the input for the Bart 2 program. I'll click on Bart 2. The instructions again appear in the description box. My target predictor is going to be the treatment variable. So I would enter in the name of the treatment variable, which in this particular data set is treat. That's scored 1-0 as a dummy variable. 1 is the intervention condition, 0 is the control condition. This is the outcome type. 1 is if I have a binary outcome. 2 is if I have a continuous outcome. Now, the outcome could be the y variable, if I'm looking at the effect of the treatment on the y variable. Or it could be a mediator, like it could be med2, if I wanted to see what's the effect of the treatment on med2. Med2 is continuous, just as the outcome is continuous. But if the mediator or the outcome is binary, then I would enter the number 1 here. Now these two boxes control special features of this program that I'll talk about in a little bit. One is and a test of the assumption of common support, and I'll explain this later. And a 1 means you want to conduct that test, and a 2 means that you don't want to conduct the test. And in this box, the program estimates the treatment effect, the intervention effect, for every individual in the study, both those who have participated in only the intervention condition and those who have participated only in the control condition. It's fairly clever the way the Bart approach estimates these effects, and I discuss them in my book. In this case, 1 means to save those individualized treatment effects in a separate data file for further analysis, and a 2 means don't save them. We often save them and then look for correlates of treatment response, and it's an interesting exploratory tool in that respect. Over here, I have to enter in the name of the ID variable for each case. And then we have the same Bayesian parameters we talked about before. Down here, I put in the equation that I want to look at. And let's suppose I want to look at the effect of the treatment on the first mediator. So I would put as my outcome mediator 1 as predicted from the treatment condition, plus the 2 covariates for that mediator, which is mCov1 plus mCov2. Again, it's important to make sure you put the treatment variable in this equation down here. I then click Register Input to generate the relevant R syntax. I copy that to the clipboard. I open up R and I paste it into R. Now on the output, what's of most interest to me is the contrast between the mean on mediator 1 for the intervention group versus the mean for the control group, because that was the question that I was addressing. Does the treatment affect mediator 1? Here's the output I get. ATE is the average treatment effect across individuals, and the statistics for it are reported here. I get the estimate, the standard deviation of the posterior distribution, and the credible intervals, lower and upper. Now I'll come back to that in just a second. Now, the intervention was designed to lower the mean score on the first mediator because it's negatively associated with the outcome. This is the control group here, and this is the intervention group here. Score of 0 on the treatment and a score of 1 on treatment. We can see that the estimated mean score for the control group was 13.81, and for the intervention group it was 11.96. And here are the credible intervals for those means. The treatment effect up here is the difference between those two means. 11.96 minus 13.81 is minus 1.84. And then again, we have the credible intervals for those. Because the value of 0 is not contained in the credible intervals, that means that the effect is statistically significant. Now, as I mentioned earlier, the BART2 program performs a test of a key assumption for treatment effect analysis, what is known as common support. I discussed the assumption in Chapter 15. Formally, common support refers to whether there is sufficient overlap between the distributions of the covariates for the intervention and control groups so that for each individual in the intervention group that has a given score on a covariate, there exists a comparable individual in the control group with a similar score on that covariate. When common support is violated, and there is non-overlap in the covariate distributions between the treatment and control conditions, accurate inferences about treatment effects can be, but they're not always, undermined. When common support is violated, it's not uncommon for researchers to delete cases from the analysis that create the problem, i.e. cases for whom a non-overlapping counterpart cannot be found. Of course, this strategy changes the fundamental nature of the inferential sample one is working with, and in turn the population to which the results may apply. Case elimination also can reduce statistical power. which can be an issue if your sample size is small. In multivariate scenarios with multiple covariates, it's difficult for researchers to know which cases to drop to achieve a reasonable degree of common support. Statisticians have developed a test in Bart called a one standard deviation test, a 1SD test, that identifies cases one should consider dropping to achieve reasonable degrees of common support. The test is computationally intensive, but you can implement by choosing one on the common support input box that I showed you earlier. The output is very straightforward, and it simply lists the IDs of cases you should consider dropping. See Chapter 15 for more details. Okay, that's the essence of the two Bart programs, and you should now have an appreciation for the kind of output that you will encounter and how to interpret it. There are a lot of important statistical and methodological details that I haven't considered, so make sure you look at Chapter 15 where I do consider them. In Chapter 15, I provide a full RET analysis using the Bart models. Okay, that's it. Thanks.